There he is. So, can we please welcome Jasper to the lectern?
Thank you, everyone. Yes, I'm Jasper, and here today to chat to you about the SSR platform that we've created at Atlassian and the evolution of the runtime we use to power that platform. Where's my mouse gone? So a bit of background. Jira started in 2002, and since then, the front end's gone through an enormous number of architectural changes. These are some of the relevant changes. So back in late 2017, we kicked off a shift toward React and away from Java templates. And then in 2018, we got our first implementation of server-side rendering. SSR has changed a lot since that version. And today we're looking at the changes that the changes to the runtime that powers that SSR and how it's contributed to cutting our page load times in half. For anyone who isn't aware, server-side rendering, or SSR, is when you run the page's JavaScript on the server and then send the resulting HTML back to the user. This usually leads to an improvement in the time taken to display some meaningful content, which is TTR, or time to render. But that usually comes at the cost of time to interactive, so when the page actually becomes clickable, or TTI. Before we get into it, though, some of the requirements for our SSR platform. In 2015, there was a big bet made on cloud at Atlassian, so shifting away from Java VMs hosted on the customer's infrastructure to multi-tenanted cloud apps. Running code for multiple tenants on the same machine brings the potential for data leakage between tenants, which we can't have. Secondly, obviously it has to be able to scale to handle Atlassian level traffic, and also has to be able to scale down to handle periods of low traffic without costing too much. And then finally, it's got to be able to go fast by just minimizing the overhead on the actual rendering. So after a few quick iterations early on, we settled onto this as the general architecture. So an instance running a node web server, which accepts requests coming from the application load balancer, and then the pool of workers to actually run the rendering and return the response back. Looking at the request flow, so firstly the request comes into the ALB. ALB sends it to the web server. Web server then picks off a worker from a pool of workers, sends the job to that, which does the rendering, which then returns the response back to the node web server, and that sends the response back through the ALB. Given the web server isn't doing too much, we can just have one of them to handle quite a few workers. And all the workers and the web server sit inside the same instance together. So we can put them all into the same scaling group. And if we've done everything correctly, then this should be able to scale up to any amount of incoming traffic, and also scale down when there's very few requests coming in. What we're looking at today, though, we're zooming into this red part at the bottom. It's the actual worker processes which are running the rendering. We've gone through a few iterations, and we're currently into the third generation of these worker processes. First one was called the classic executor. So as before, main requirement, can't have any cross-tenant data leakage. So with the same process serving many requests, an SSR making external fetches outside to grab user data and then put that into the HTML to return back. Need to be very careful about each request being isolated from the rest of the requests. So in the classic executor, we used a node VM context to execute each request. And node VM contexts are essentially just eval functions, but with separate globals. So by using a new worker for each request and then cleaning it up after each one, we can make sure there's no cross-tenant data leakage. Having a look at how the actual request gets handled, similar to above, comes into the node web server and then gets sent to the node VM, which runs the request. Then the worker makes any external fetches out to the internet, which is the cloud over there. Any of that data gets returned back to the node VM, which then finishes the render and returns the response back to the user. After the request finishes, then we send a message to the controller just saying that we've finished, and then that cleans up the worker. And then once the worker's been destroyed, then we refill that pool. So it's a pretty simple way just to ensure that we have fresh context for each request and there's no leakage. This works really well. To give you an indication of the kind of performance that we got, for Jira, there was a period where we had to turn SSR off for some time, and that took page load times from 1.8 seconds to 4 seconds. So it shows that SSR is improving performance by 2 times. With Confluence, they recently went through a big performance push, and using SSR got page load times from 14.5 seconds down to 5 seconds. And then Bitbucket saw a similar increase to Jira, where the code review page load time went from 4 seconds to 2 seconds by implementing SSR. So there's a lot of potential gains to be made. But we have very big bundles at Atlassian. So some of them are 200 megabytes big. Reading a 200 megabyte file, parsing that, compiling it into JavaScript, and then running that JavaScript to get it ready takes about 200 milliseconds. Putting that into the request path is a pretty huge performance hit. So that's why we maintain the pool of workers. But even then, spending 200 milliseconds loading up each node VM after every request chews up a lot of CPU time and drives up a lot of cost. So we need a way to minimize that refilling time. Introducing the second generation, which is the SnapVM executor. So our team looked at using V8 Engine's snapshot feature, where you can load up and execute some JavaScript, then take a snapshot of the JavaScript heap, save that snapshot somewhere into memory. And then next time, when we want to load up a new context, we use that snapshot as a kind of template to create the new context. Just makes it much faster to speed up. There's an npm package called isolated VM, if you want to have a look, which is perfect for this. So now when starting up the SSR platform, the controller first creates this snapshot, and then for each subsequent worker that started up, that's much, much quicker. So it takes loading up a bundle of the same size, 200 megabytes, from 200 milliseconds down to 30 milliseconds. Huge performance improvement. But it comes at a cost. So it's fantastic to get that kind of speed up. But the context that this isolated VM package creates are raw V8 contexts. They're not node processes. So we don't have any access to like node APIs like fetch or timers or consoles. We have to implement all that stuff ourselves. It becomes pretty difficult to then render anything if you don't have those APIs. For the most part, though, it's okay. So instead of actually implementing our own version of each of these APIs, we can just pass the request off to that main node web server that completes the request and returns us back the response. So now what the request flow kind of looks like is something comes into the node web server that passes off to the SnapVM worker. SnapVM worker then needs to fetch some external data. So it sends those requests back to the node web server, which then requests out to the internet, gets the data back, returns it back to SnapVM, then returns it back to the web server, and finally returns the render response. So it's kind of a bit of a complicated request flow, but keep in mind the main change here is just shifting work out of the SnapVM worker and then into the main node process. This worked great. So with Jira, we got a time to render improvement of between 50 and 300 milliseconds, depending on each page. But the main improvement came from efficiency. So we're able to now handle about 30% more requests per instance, which dropped our infrastructure cost by 40% just by making this change. And then Confluence also saw a similar huge improvement in TTR and around 30% drop in cost. But isolated VM is fantastic, gave us enormous improvements, but it's not maintained anymore, unfortunately. So not supported past node 20. So now we need a way of future-proofing the runtime and still using these snapshots. Introducing the third generation, SnapVM Native, which is the newest one. So SnapVM Native is a very minimal runtime that we implemented straight in C++ and just interacts with the V8 engine directly. So it disconnects us from any node versions and any external dependencies and lets us implement everything ourselves. Within SnapVM, we were already working with these non-node contexts, so we could keep a lot of our old code and just have this wrapper around V8. Some of the results from this one, also fantastic. So TTR was improved by about 50 milliseconds in Jira and 300 milliseconds in Confluence. But the main benefit came from being able to work directly with V8. So now we can do a lot of hacky and tricky things to try and speed up requests and have a lot more control over what's really going on. Also lets us remove some of the overhead from isolated VM. So there are a few things in there that we just didn't need. But now, no solution is perfect. So you recall from earlier with SnapVM that because it's not a node process, we're shifting a lot of the things out of the SnapVM workers into node to then be executed from there. So you can see in this diagram, there's only 2 external fetches coming from each SnapVM worker. But in reality, we have 12 workers, and each of them making about 20 requests, external requests for each incoming request. So you can kind of see where this is going. The main node process is just a single threaded process. And so as soon as you have multiple requests going on, immediately gets overflowed, and we get throttled. This is what a table of processes looks like just a running instance of our runtime platform. Zooming in, you can see the main node process is at 94% CPU usage, and then all the others are sort of 30% for 3 of the SnapVM workers, everything else at 0. So we're wasting a lot of resources and could be definitely optimized a lot more. This is something that we're dealing with right now and feeling the effects of, unfortunately. So the fix is just to shift all these hacky things. We're sending the requests off the main node worker, moving that all into SnapVM. Hopefully should fix things up. And that's about it for me. So thank you everyone for listening. Hopefully that was a good journey.
Jasper, that was amazing. Those speed improvements are phenomenal. Have you had any feedback from users?
Sorry, say again?
Have you had any feedback from users?
Better performance, I suppose, is the main one. Pages loading faster.
Excellent.
Yeah.
Is Sam there with the microphone to ask the audience?
I am, yes. Do we have any questions? Yep.
Thanks for the talk. Did you at any point look into things like V8 compile cache, or I think newer Node versions might have something similar to V8 compile cache built into Node. It's behind some sort of experimental flag.
Haven't looked into V8 compile. Is that a new Node thing?
I think V8 compile cache is a fairly old Node package. We have in the past encountered some weird bugs around V8 compile cache, and I think it is used indirectly by some other packages that we use at work.
Interesting. Okay. No, we don't think we may have. I'm not sure. Possibly, but yeah, it seems like snapshots work quite well, so we'll probably keep going with that one.
I had a question just about the sort of isolation requirements. So like my understanding was the main reason you want to use those VMs is to have like tenant isolation, right? But then if you're pushing all of the fetch requests through the single node process anyway, like is that undermining the isolation, or like what's the benefit of having, some work be done in the worker but still having sort of these external fetches be done in the parent process?
Yeah, somewhat unavoidable problem at this stage, I suppose. I think it is still able to maintain solid isolation. It's all kind of going through the same channel, but I don't know, seems to be well isolated at this point. Yeah.
Is it just the isolation, or is it also that like because you're splitting into multiple workers, I guess you're getting some level of like multi-threading as well? Is that just like is that the main reason, or just like a side benefit, or
for the initial
yeah,
or the final one? Yeah, I mean, having multiple workers would just kind of spread the CPU load across the instance as much as you can. Just try and get better performance, I suppose.
Yeah.
Yeah, as you see, it's not really working too well on the Snap VM one, just everything loading into that main node process.
Gotcha. Yeah. Any other questions? Oh, yeah, we do have one. Yep.
Thank you. Why you didn't use Next.js for server-side rendering?
We did consider it at the very start of kind of starting the front-end platform team, but it turned out to be if we rolled our own solution for front-end platform, then we can have our own kind of integrations, integrate better into authentication between different services, and really refine things to work best with the current Atlassian stack. And actually, with having Jira as such an old product from 2002, a lot of legacy code there that we had to integrate with. So shifting to something like Next.js wouldn't quite have worked with some of the requirements that we had. Yeah.
Thanks.
Anyone else? Oh, yeah. All right, let's give another round of applause.
Thank you very much. We'll talk to you very soon. Thank you.